Today, applications of dot and cross product, finally, through all this dot and cross product, we'll see where some of this is used. I won't begin to convince you that this is all the things you can do with dot and cross product. It just gives you a little taste here before this chapter wraps up, exactly what dot product and cross product do in real world stuff, not just in sort of abstract vector thinking. So first thing, the word work is commonly applied to any activity that requires physical exertion or mental effort. In physics, however, the word work has a narrower meaning, meaning only certain things count as work. And I'll explain that before I even get into the box here, is that for you to have done work in physics, work means something has moved. You've transferred some amount of energy to it. So not all things that we would call work, necessarily something moves. But in physics, work means some energy was transferred by moving an object. So work is done whenever a force acting on an object causes displacement of the object from one position to another. The work done in moving an object is given by the component of the force in the direction of the motion multiplied by the distance traveled. Basically, you're saying how much force did you move something with and how far did it go? That's how much work you're going to do. Let's think about that for a second. If you push a box across the floor and you push it twice as far, that should be twice as much work. So the distance is part of work. Also, if you have to push something that's twice as much mass, which means it has twice as much force that you have to use, that should be twice as much work. So both force and displacement are involved here, and we actually multiply those two things together to figure out how much work is being done. Now, why is the cos theta in there? Is because we have to, and you'll see in the first example, why is cos theta in there? We only want the force that's in the direction that we're going. This is really dot product. That's what this is going on here, is dot product. How much of this force is operating in the direction we're going? So W is the work done, F is the force acting on the object, D is the displacement, and theta is the angle between the force and the displacement. The unit of work is called the Newton meter. It's so common that we actually give it its own special name, the joule. And joule, for you physics people, is amount of energy that we're transferring. And this work is going to be a scalar quantity. It's going to be a number. So a crate is on a ramp, is hauled 8 meters up the ramp under a constant force of 20 meters per second at an angle of 25 degrees to the ramp. Find the work done. Just need a little picture here to establish what's happening here. Here's my ramp. And for you physics people, you might be worried about the angle of the ramp, but this particular case is such that we don't really need the angle of the ramp because there's the displacement going up the ramp there, and then there's a force acting at 25 degrees to the ramp. So it's the perfect, they've actually given us the exact angle that we need here. And so work is force dotted with displacement. That's what we said the definition of work was. So in our case, we're going to take the magnitude of force, multiply it by the magnitude of displacement, times cos of the angle between us. And maybe now you can see why it had to be cos of the angle between us, because we want to know how much force is actually pulling the crate up the ramp. Not just this random force sticking out in this direction right here. We don't care about that. What we care about is how much of that is actually doing work on the crate. So the force applied is 20 newtons. The displacement we're talking about here is 8 meters, and the angle is 25 degrees between these two things. When I multiply that all together, I get 145 Newton meters, called joules. So 145 joules has been transferred from the person, or that's doing the pulling here, into energy on the crate. For you physics people, it's really transferring some of this into gravitational potential energy. But yeah, you don't have to worry about that too much now. The important thing is 145 joules of work was done. We can also use dot and cross product to find area of a parallelogram. The area of the parallelogram is found by multiplying the base and its height. The base is the magnitude of u, so that's how long the magnitude, the length of the bottom will be how long the vector u is. And with a little bit of Sakatoa, you can find that the height of the parallelogram will be magnitude v sine theta. You can see in that little triangle there that you get magnitude v sine theta. And so what we get is the area of the parallelogram is u v sine theta. And does that look familiar, u v sine theta? Well, you bet it does. That's cross product. That's exactly what's happening there. So if you want to find the area of a parallelogram, you can just do magnitude of u cross v. You just have to find the magnitude of u cross v. So it says find the area of this following parallelogram. Well, what we will do to find the area is magnitude u, magnitude v, times sine theta, the angle between them. So it's 13 times 8 times sine 30. So I'm using that as my u and that as my v. And when I multiply those together, I get 52. Units weren't given in this question, so whatever they are, units squared. A slightly tougher question that shows off what this thing can do. The points 1, 1, 1, negative 2, 0, 4, C, 1, 2, negative 3, and D, 4, 3, 2 are the vertices of a parallelogram. Find the area of ABCD, which is the parallelogram. So let me just draw this parallelogram here. And this is A, B, C, D. A is 1, 1, 1. B is negative 2, 0, negative 4. C is 1, 2, negative 3. And D is 4, 3, 2. Now to find this area of this parallelogram I've got here, I need two vectors, u and v. And the two vectors I'm going to use are, let me draw them on here. This vector here, that'll be my u in the u cross v. And then the v is going to be this one here. So I'm going to call this u, call this v. And my u vector here, let me just look at that, is 1 minus 4 is negative 3. 2 minus 3 is negative 1. And negative 3 minus 2 is negative 5. My v will be 1 minus 2, which is negative 1. 1 minus 3, which is negative 2. And finally, 1 minus 4, which is negative 3. Why did I have that u and that v? Because what I really want to do is find area, which is the magnitude of u crossed with v. So I want the magnitude of u crossed with v. Here comes my cross product. Hopefully you've done some practicing on cross product, so you can do these fairly quickly. I'm going to use some of my space over here. I know from doing this question before, I won't need much space over here. So let's see. U cross v, negative 3, negative 1, negative 5 with another negative 3, negative 1, negative 2, negative 3 with another negative 1. Oh my goodness. Okay, so 3 minus 10, I get negative 7. Oh, I see what's gone wrong here. Let me just fix this up. This v here wasn't right. That v was 1 minus 2, which is negative 1. 1 minus 4, which is negative 3 here. Then negative 2 and negative 1. I had those reversed. I was writing them in the wrong spots there. So then the second vector is negative 3, negative 2, negative 1, and a negative 3 there. Okay, so now, so now I get 1 minus 10, which is negative 9. And I get, let's see, 15 minus 3. 15 minus 3, which is 12. And I get 6 minus 3, which is 3. There we go, that's better. And now to find that area, I need that the magnitude of that, which is 81, 144, and 9. Square root 234 is the area of that parallelogram. Now, if you just want the triangle ABC, which is just half of that. So the area of triangle ABC is root 234 divided by 2. And again, no units given here, so it's just units squared, units squared. So finding area of parallelogram is the second application we look at today of dot and cross product. The third one is torque. This is a big one. When a threaded bolt is tightened by applying force to a wrench, the measure of turning effect of the force is called torque. So it's how much a wrench, how much force you're able to, how much turning effect you're getting from a certain force. And the magnitude of turning effect depends on two factors. How far away from the bolt you're applying the force. So the farther out you go, the more torque you get. And it also depends on the magnitude of the force. And so if you want to find the magnitude of torque, we're just actually finding R cross F. This is exactly what cross product is for. It's for finding torques. And you're just doing R cross F. And here, the magnitude of torque is found by R, F, sine theta, magnitude R, magnitude F, sine theta. One little thing here, R is the radius vector from the center of rotation to the point where the force is applied. And F is the applied force. And theta is the angle between R and F when arranged tail to tail. So you just got to set this up just right. Because in the picture here, they've given a wrench providing some torque here. And this here is the radius vector from the point of turning out to where it's being turned. There's R. And then the force vector is out here. And so they really should be tail to tail. In this particular case, it doesn't actually matter because that angle stays the same when I slide that down there because of where they've given the angle. But you got to watch out for the angles. The angle has to be between R and F here. And this one, they were nice. They gave us the angle in the right position there. But if the angle's in the wrong position, make sure you slide it so that they're tail to tail. So to find the magnitude of torque, we go magnitude of R cross F, which is magnitude of R times magnitude of F times sine of the angle between them. I've set it all up right here, so I got 0.2 times 50 times sine of 70. When I multiply that all together, I get 9.4. And weirdly, it is a joule here, newtons times meters. Now, what directions does this force act? If you put your fingers along R so that they'll wrap towards F, your right hand, it's into the page. And what angle would give maximum torque? Well, 90 degrees, because sine of 90 gives 1, gives you full effect. Okay, so use those three examples to help guide you through the homework, and really gives you a good flavor for how this stuff is used in real life.